Hi, everybody. So today we're going to be doing the second part of endogeneity and simultaneous equation stuff. And I hope to show you. I'm going to not share that way. Hopefully this will be useful maybe for projects and just locking in the logic. Really, I'm going to focus a lot today on the logic and understanding what's really happening with simultaneity, which I know I've reinforced a couple times now. The very first lecture was about simultaneity. Of course, a couple weeks ago, we went deeper into endogeneity. We're going back to simultaneity and simultaneous equations, and I'm going to just use this example throughout the lecture today. And part of that, I'm going to simulate the data. The reason I'm going to do that is I think that just looking through actually, and many of you did this well on your most recent homework, but just talking through a simulation of a simultaneous system and why that leads to endogeneity, I think can be really useful. And then the other thing I'm going to show you guys today is we can implement machine learning and combine those things with two-stage models like two-stage least squares. So I was going to show you some of that. That could be a fun thing to do to a project. So I showed you guys an example of a project last time. That project is very similar actually to this system of equations. Um, and you could do something like I've done in this notebook today and compare the results of something like two-stage least squares to two-stage machine learning, as broadly some of those things are called. And I'll just show you one example of that today. You could go very deep down that rabbit hole because we could have many ways that something like machine learning type algorithms are interacting with things like two-stage least squares. Finally, I want to encourage you. I have met with several of you about your projects, but just keeping in touch with me to talk about what you're working on for your project, I think would be great. I'm happy to meet with you regularly as I do with some students about those. You do have to present it publicly, so we want it to be good. If the grade isn't a good enough reason to do a good job, then maybe presenting it publicly to other students and professors is good motivation. So I would love to chat with you about it, see what you're thinking about, provide comments and feedback, and just brainstorm with you, really, because that I think is where the best projects come from if we have a chance to brainstorm about different opportunities. But anyway, let's get into it. So, first, I'll just show you this model of endogenous housing and labor costs. And this would be a great thing to think about if you're thinking about something with a simultaneous system for your project. So we're starting out by just setting up an equation saying housing cost is going to depend on demand, which we're going to just proxy by the number of sales. We already know that there could be issues with that from other lessons, like this is basically putting quantity and price on the same in the same equation. We're going to ignore that part of the endogeneity issue for this particular example, but if we were collecting data on that, we would probably want to be concerned about that. So we have housing cost, which is how much people have to pay for pricing housing. You can think of it as price, but maybe like an index that includes whether you're renting or buying. Maybe it would be a broader measure of housing cost. So that's going to depend on sales, how many people are looking for homes and looking for apartments, maybe could be included in that. And then construction costs, of course, if construction costs are high, that probably will lead to higher housing costs because even if people are paying premium prices, it may be as hard to respond to that demand by building more houses. Construction and cost in turn is we could break that down and say, well, maybe that depends on material prices and labor costs. That makes perfect sense. I have to buy materials to build houses and hire workers to build houses. Finally, this is where the endogeneity issue and this problem comes in is labor costs. There's a possibility that those, in fact, depend on housing costs. If housing is more expensive, laborers in that area likely will also be more expensive. So the system of simultaneous population regression equations hypothesizes that housing costs in geography I and time period T depends on construction costs and the number of homes. So this is just summarizing what I just told you. We can use substitution to show how construction cost equation depends on housing cost, right? So we could substitute material prices and labor costs into this equation. Or sorry, we could substitute away labor costs. So we're substituting here to get housing costs into this construction cost equation. And then we see, okay, construction cost depends on housing costs, right? So this is an independent variable in equation one, but it's pretty straightforward to use equation three to show that construction cost right there depends on housing costs. And that's going to be a pretty apparent, like that's going to lead to an endogeneity issue, certainly. We could really explicitly show that that leads to an endogeneity issue, making this substitution where now we have housing cost is a function of housing cost. Now notice that when housing cost is higher, that causes housing costs to be higher. So those types of things, that's going to be an error term issue, and that's going to lead to covariance between construction costs and our error terms. Because again, this is basically construction costs right here, right? So if the dependent variable shows up on the right-hand side of the regression equation, we definitely have an endogeneity issue. So that would be one way if you're setting up a system of simultaneous equations. That might be a nice way to express that for your project on your poster or something, if you would end up with a project like this. Now, finally, we can solve all this for housing cost and make housing cost a function of only exogenous prices. That's important to think about because this is something we need to think about if we're going to actually simulate and understand what's really going on with simultaneity in this system of equations. We have to be very careful about the order with which we simulate data. I think maybe a couple of students had issues with this. Definitely in the past, students have had issues with this. I had issues with this when I was first making this lecture because it is pretty complicated to think about the ordering that variables need to be created in to make this simulation work in the sense of have a simultaneity bias problem and then fix that problem with two-stage least squares. So let's go just ahead and look at how we had to simulate this data. So I'm using 5,000 observations. I'm setting a random seed because that way I'll be able to get the same results back when I run the code again. So here I'm just setting up the population parameters. That's really the key to simulation is that we are going to know what the answers to our questions are. This is the parameter of interest right here. We're just setting the effective construction cost on housing costs. That's the parameter of interest, right? Because we're going to note that we also get bias when we estimate beta 2. That's called smearing, which I mentioned last time. But really the key is we know we're going to get a bias coefficient here. We're setting beta 3 at 1. So then we're going to ask, do we actually observe 1 when we run regressions to try to estimate that known population parameter? Why do we know it? Because we're simulating it. Those are really the trade-offs. And if you're thinking about anything related to endogeneity, we should definitely chat about, maybe you still don't know, is it better to do a simulation or try to collect observational data? There's trade-offs. So there's benefits and costs to both of those choices. The main benefit to a simulation is we know the truth and we can compare our results to the truth. And that gives us sort of a way to think about a robust conversation. Of course, the main cost of using a simulation is we're not using real data. That might be less interesting to some people. I think the best projects in the long run, and right now I'm not talking about your poster project, the best data science projects in the long run use both. So, okay, I'm trying to answer a real question with real data. That real data probably has some issues. In order to understand those issues before I approach the problem in the real data, I will use simulation. So that's probably too much, although I mentioned last time, and I think in my announcement about how you could mix those even for your poster project, what I just described is pretty intensive for a single semester poster project. But I think that's really what I want you to take from the class is the usefulness of simulations combined with applied work with real data, because the simulations help us understand what the techniques are actually doing. So here's equation 3. So again, I'm just setting up the population parameters here. Now I can just create my exogenous variables. They're created outside the system. I create them outside the system right here. I just sort of picked some numbers that I thought were feasible. Now the air terms here, I'm not forcing the air terms to be correlated with anything here. So I want to make that clear. These air terms, when I create them, are not being forced to be correlated with construction costs, for example. This is the housing air. Here, we don't have correlation necessarily. We haven't created construction costs yet. That's going to be the key. But I'm making this air for now is sort of independent of the system. But then here we go. Now we're going to create housing costs, because what does housing costs depend on? Here is how we're creating housing costs. We're not using construction costs because we haven't created it yet. We're using just our exogenous variables to create housing cost. So there's that. Now we can generate endogenous variables. So we know labor cost depends on housing costs. So that's why we needed to make housing costs first to create that. And then construction cost here also depends on housing costs, but really through housing costs impact on labor cost. And so that's why I'm creating labor cost first, and then housing cost, construction cost, who's impacted by housing cost. There's housing cost, that's impacting labor cost. Here's labor cost, that's impacting construction cost. So that is the mechanism by which housing cost is reverse causing housing cost. Housing cost is reverse causing construction cost through these two equations right here. Now we've generated all the data. So now we have all of the data we need to run a regression specifically, and a couple people didn't do this, and I made comments about it, but it's important, especially if you're thinking about doing a simulation for this, or even if you're doing this on observational data. You should definitely run the standard OLS version as if there is no endogeneity problem first for comparative reasons. Now we're going to do that here to simply see, do we get a bias estimate? Now, we don't know if we're using observational data, not as like we're not doing a simulation, then we don't know what the true number is. That's the entire point. We're trying to estimate the number that we don't know. So it's still important to do this for comparison. Did my estimate change? If your estimate doesn't change at all between OLS and 2SLS, that leads to more questions, really. Maybe there wasn't a simultaneity issue. Maybe you didn't fix it. So those are the two possible interpretations of that. When you're using observational data, it'd be really good to have a theory. And if you have a theory, then you can probably sign the bias related to simultaneity. If my theory about simultaneity is correct, then that should bias my coefficient downwards or upwards. So at least in that case, you could compare your raw OLS estimate to your two-stage estimates and see, is it moving in the direction that I thought based on my theory about the bias in the system. So it's important to run just the standard OLS one to see for comparative comparison later. Now we set our coefficient of interest beta 3 at 1. So beta 1 is our constant, that's 65. X1, that is our coefficient on sales, that's 0.5297. Our coefficient on X2, construction costs, is 0.8129. So about 20% too low, right? Because 1 is what we set it at. We can look at this one too. So sales is 0.5. We're getting too big of an estimate for sales. Notice in both cases, the true parameter is not even inside the 95% confidence interval. Let's check with the intercept. None of our estimates, the truth is never within the 95% confidence interval in any of these estimates. This is a large data set that I created. 4,997 degrees of freedom. So it's definitely not a sample size problem that's causing this bias. So there you go. That's pretty explicitly showing the bias of our OLS results in this system. So let's go down and see what happens then if we use two stage least squares for this same estimate. To our first stage, we're going to use all of our exogenous variables. So material prices and sales, because sales is the other exogenous variable. Now, notice that in our system, sales does not directly impact construction cost. But in two-stage least squares, we use all of the other independent variables, the exogenous ones, that are in the regression equation of interest, which is that construction cost equation. So that's why sales is included here. Material prices is really the one we expect to get more action out of, because that's the one that directly impacts construction cost, but is not endogenous. Sorry, sales isn't endogenous either. But up in our main system, we have this exogenous variable. We expect that from our theory to directly affect construction cost. Sales were the main reason we're including that in our first stage of our two-stage least squares is you need to include all of the other exogenous variables in the equation of interest, this one, in the first stage. So that's again why sales is appearing here, and then material prices. And then we just OLS on that. So construction costs is our dependent variable. This is just our set of independent variables right here. So we fit that. So we can assess the first stage results right here. Our R squared is a little over half. You can't really know actually if it's good or not. That seems big enough to be relevant. We're saying explaining more than half of the data, half of the variation in the data. The F statistic, the model is significant. So the overall model is statistically significant. If the model wasn't statistically significant, then we'd probably definitely be concerned about a relevance issue. This model is so significant, like the R squared isn't too high, but this model is so significant that maybe we're beginning to be worried about exogeneity already at this point. So, and that is always a trade-off. We do not know whether we have true exogeneity. Now, in the simulation, we do know because we set up the simulation to those variables are truly exogenous in the simulation. So we know from the simulation, if you're using observational data, you have to just assess. That's another really good reason it's good to compare your two-stage results to your OLS results, because if at least you have a theory about the direction of the bias, and then your results are updated in the correct direction based on that theory, that's probably the strongest evidence you're going to get in observational data where you don't know the truth from a simulation. But this looks, I'd say, pretty good for a first stage. If we were looking at observational data, these results would look pretty nice to us. Relatively good R squared, but not so high that we begin to be worried again directly about endogeneity. Because if this is like 0.99, it's almost certain that it's not exogenous. Because the only way it would be exogenous is if the only endogeneity issue was living in just a tiny proportion of the variation. Probably you don't even have that big of an endogeneity issue in the first place if it's living in that small part of the variation. So one thing just to say really quickly on that first stage results, I just don't know if I said it. This again, these are not our coefficients of interest. This one is, that one's clearly biased. These are biased too. That is called smearing. When we don't just bias the coefficient of interest, it biases all of the coefficients in the regression of interest. We just check the first stage from the 2LS here, 2SLS here. Now here is our second stage results. And now we do get a much better result. 1 is inside of our confidence interval. 0.5 is inside of our confidence interval here. And 50, the intercept, is inside of our confidence interval here. So two-stage least squares worked. So I just wanted to show you, I feel like that's maybe a cleaner, pure example of both the theory, the simulation, OLS, ignoring endogeneity or simultaneity. First stage assessment, second stage is unbiased. Now, I also wanted to tie this. A lot of you have brought up different types of machine learning algorithms over time. And I just wanted to point out that, or sorry, before I get there, here's a graph showing the two different lines. So our OLS biased one and our 2SLS one that's consistent. So it's an unbiased, consistent estimator. Now, to make this chart, I wanted to just point out that because we have a multivariable regression with sales and construction costs in it, we needed to hold sales constant in order to make this chart. So we're just holding sales constant at the mean right here. That's what that's doing. And then that's, so I just wanted to show you that I thought that was a cool way to express, because some of you might doing something where you're fixing bias and you can compare the two different relationships sort of nicely for your viewer in that way. So now getting to two-stage least squares to what's called two-stage machine learning, which encompasses a lot of different things, but I just wanted to show you a really quick way you might think about integrating machine learning into these types of models. So we can always use flexible machine learning models for the first stage of our regression. We use OLS, which is the standard for two-stage least squares and is the standard if you think you have a linear relationship. We simulated a linear relationship, so that made sense for us to use two-stage least squares. There's all types of cases where you might be better off by using a machine learning algorithm to do your first stage predictions and using a machine learning algorithm to do your second stage predictions as well. We're just going to do the first stage here. Whether those are the right course of action will depend on what your beliefs sort of about the data and about the theoretical underpinnings of the system. So the goal is to still isolate. The goal essentially in this context, I mean, the goal could change with context, but in my context here, the goal is still to isolate variation in the endogenous regressors. So construction costs in this case, that is exogenous. So that is still the goal. The key is to avoid overfitting that would naturally result in the first stage. So you might have a bunch of good reasons to use machine learning in your first stage, but we know that machine learning algorithms are likely to overfit. So overfitting the first stage model will likely violate the exogeneity assumption, which is just the same way, the same reason if we got a super high R squared in the first stage, we're probably violating the exogeneity assumption. Well, if we use a really hardcore machine learning model that's awesome at predicting the first stage, then we're probably bringing the endogeneity over with us. So we have to be careful of that. And that's a key to two-stage machine learning. So one fix for this, and there's many different ones, but one very common and simple to understand one is cross-fitting the data. So split the sample into folds, so maybe two folds, just randomly split the data in half. Estimate the first stage and outcome models on one fold. So within sample, do it on the first half of the data. But then, so we're estimating the model there, but then we're predicting on the other fold of the data. So that's going to help us avoid overfitting. So the exact same way we essentially often avoid overfitting in many machine learning algorithms when we're iterating between testing and training. So the same idea to avoid overfitting in the first stage of a regression. We could do more than two folds. We could do this on many different folds. Whether you wanted to do it on more than two folds would depend. And we can I'll talk a little bit more about that after we look at the results of this. So there's going to always be a trade-off because two-stage machine learning will involve more of a black box rather than a theory-based exogeneity. Now, maybe I'm being a little too fast and loose with that because you could imagine motivating a machine learning algorithm with theory. So that's maybe too bold of a statement right there. But in general, that could be kind of true. Like, oh, I'm using machine learning because I don't really understand the nature of my first stage. I don't think it's linear. So that type of reasoning is more of like, so I'm going to put it in the black box, which is fine, but you'll want to be careful about assessment of things like whether exogeneity is really there. In this model, I'll just tell you right off the bat, we're not going to get as good a results from our machine learning version because I simulated the data linearly. You'd really want to be thinking about this. There's definitely the possibility that there's some super crazy relationship between construction costs and material prices that's not linear at all. And maybe you can't even come up with a good functional form to be thinking about material prices and construction costs. Those, if you're thinking along those lines, those are the reasons we might be moving towards a machine learning type model for our first stage. So the algorithm again is pretty simple. To the extent you've run machine learning algorithms, all we're doing is essentially using machine learning on our first stage, making predictions using machine learning, using those predictions in the second stage. So that's really the only difference that's happening here. So I use a random forest model. And then we can see here is our R squared from the first stage. So it's a little bit less of a fit, but that's out of sample, right? Because we're applying on the out of sample. Here is our coefficient of interest. That is farther away from the truth than, because remember, the true parameter was 1. So that was the construction cost parameter that we set. We got about, let's see, we can just check it out. We got this 1.0051, so very close. This is a little bit more distant downward bias, so in the direction. Really what's happening here is we're doing a better job fitting that, and we're bringing across some of the endogeneity. That's essentially what's in. It's easy to see here because it's a simulation, and this coefficient is sitting between our very biased OLS1, our better 2SLS1, and what's happening here is we're just bringing through some of the endogeneity from the simulation because the random forest algorithm doesn't know we simulated this data using just a linear model. So it's not doing as good of a job as the linear model at just getting the exogenous part of the variation out. Okay. So, and you could go crazy with this. Like I said, you could do a first stage machine learning algorithm and a second stage machine learning algorithm. If you had a reason to believe that there was an endogeneity issue and it was impacting your second stage results or the results you were trying to get at, there could be very cool, maybe pretty intense for a project, very cool things there, even in AI algorithms because we can imagine endogeneity being an issue when people are prompting, asking for answers in AI. Endogeneity definitely could be an issue there in terms of the AI predicting best responses and things. And those are really the broader things that I want you to think about because it's easy in data science to just get sucked down into the rabbit hole of running different models, trying to know all of these different models. But really, AI is good at those things. So really, I think the way the world's changing, it's really time we need to step back as data scientists and say, where is the human sort of value proposition in all of this? And I think it is actually stepping back, thinking about things like endogeneity. I often refer to as you need a theory. This needs to be tied to theory for us to even know. And so those are the things that AI is going to be struggling with because they involve more creative reasoning and things like that. So I think this could be a very cool thing to approach for your project. Please let me know if you have any questions about this, but I'd love to talk to students about their projects in general as we approach deadlines for those things. So don't hesitate to reach out. And I hope you enjoyed the lecture, and I'll see you later.